So, this is VLSI data conversion circuits lecture 39. In the last class we looked at various flavors of integrators. Now, let us look at another important aspect of these integrators, namely device noise. So, if we take the example of the single stage structure, it has several noise sources. One is the resistor itself, and the effect of the resistor can noise in the resistor can be thought of as a voltage source in series with the resistor. The spectral density of this noise source is 4 kT R volt square per hertz. The transconductor, on the other hand, can be thought of as a noise current being injected at its output, and the spectral density of this current SI2 is given by 4 kT times Gm times some factor eta, which is called the excess noise factor. It depends on the circuit details of the realization of the transconductor, but in principle the transconductor noise can be modeled by current source of this form. And this makes sense, because if I wanted to realize 2 Gm, what I would do is take two identical transconductors and put them in parallel, right, and the noise current that would be injected at the output, the spectral density would go up by a factor of 2. So, it is a self consistent model. Now, these two noise sources obviously cause the output voltage here to be in error, alright. So, to find the effect of these noise sources on the output, we simply use superposition. Let us also assume that we have the zero cancelling resistor here, alright, equal to 1 by Gm, so that the feed forward 0 has gone away. We will ignore the noise contribution of this resistor, alright, and try and compute the output noise due to both these noise sources. So, before we do that, let us find the virtual ground voltage. The exact virtual ground voltage is given by, what is the input impedance looking in here? What is the input impedance looking in there? How will you find the input impedance? You will apply a voltage and find the current. So, if you apply a voltage, test voltage here, what is the current that flows like this? Gm times V test. So, the input impedance is one by Gm, correct. So, the input impedance is 1 by Gm. What would be the exact voltage here? this voltage will be Vi times 1 by 1 plus GMR, correct. So, the current that flows through the input resistor is given by Vi by R times if the voltage on the right of the resistor is Vi by 1 plus GMR and to the left is Vi, what is the current that flows through the resistor? It is Vi by R times GMR by 1 plus GMR, alright. That current flows through the integrating capacitor, okay, and what will be the drop across this resistor now? Vi by 1 plus GMR. So, what will this potential be? Please note that the virtual ground potential is Vi by 1 plus GMR, correct. The drop across the 1 by GM resistor is Vi by 1 plus GMR, but in which direction? In this direction. So, the potential to the right of that resistor will be 0. Is that clear? So, the output voltage is simply this current flowing through 1 by SC. So, VO is this. So, VO by Vi is therefore minus 1 by SCR times GMR by 1 plus GM. And this makes sense because we know that that resistor was there to cancel out the 0 in the first place, all right. Now, the transfer function from the noise source to the output is the same as that from the input to the output. So, the noise spectral density at the output due to the is nothing but 4 kT R times, if I call this H1, it will be mod H1 of F the whole square, right. So, this noise source we are done with. Now, we need to worry about what the effect of this noise source will be on the output. All right. So, how would one calculate the effect of IN2 on the output? Let us calculate this voltage. Let us assume that this voltage is Vx, correct. So, this current will be Vx by R which I will denote by G. Okay. So, this current will be the same as that, correct. So, this is Gm, or rather this 1 by Gm, okay. So, this current will be G times Vx. This current will also be, this will be Gm times Vx, okay. So, In2 therefore must be G plus Gm times Vx all right. What are we interested in, however? We are interested in VO, right, okay. So, can you help me evaluate VO? Pardon, Vx is nothing but it is simply V naught into this, I mean the same current flows to this branch and this branch, right. So, it is nothing but a voltage divider. So, Vx is nothing but VO times R by 1 plus, I am sorry, R plus 1 by SC plus 1 by Gm, okay, which means that In2 is G plus Gm times R times V naught divided by R plus 1 over SC plus 1 over Gm. Okay. So, VO is nothing but, or SVO, the output noise spectral density is given by 4 kT Gm times eta, which is the noise spectral density of In2, multiplied by the square of the transfer function, which is R plus 1 over SC plus 1 over Gm divided by G plus Gm times R okay, which can be simplified further, or this whole square, correct. This must be J 2 pi f c, since we are interested in spectral density as a function of Hertz, right. So, this is nothing but GMR plus 1 over Gm, all right, plus 1 over J 2 pi f c divided by 1 plus GMR times 4 kT eta gm, which is approximately equal to, I mean if you choose GMR to be much greater than 1, which one would do anyway to make sure that the unity gain frequency of the integrator is close to 1 over RC, this spectral density will reduce to 1 over GM plus 1 over J 2 pi FC divided by, if GMR is much larger than 1, you can neglect the 1 in relation to the GMR. I am sorry, this is R whole square divided by 4 kT eta gm, which can therefore be written as 1 by gm plus 1 over J 2 pi F R C times gm whole square into 4 kT gm times eta. Let us see the intuition behind this result. As frequency tends to infinity, what would you expect without doing all the math? The noise voltage here, or the transfer, I mean is basically this noise spectrum multiplied by the transfer function the whole square. The transfer function is nothing but the output impedance looking into the transconductor, right. At very high frequencies, what would be the output impedance? No. At very high frequencies, what is happening? The capacitor behaves like a short circuit. So, whatever voltage you apply here, almost all of it appears at the virtual ground node, correct, because it is a series divider between this 1 by Gm and this R. The 1 by Gm, as you know, is very small compared to R. Is that clear? Which means that this voltage will virtually be what you apply here at very high frequencies, which means that the current drawn by the Gm will be Gm into whatever test voltage you apply there. So, the output impedance at very high frequencies must be close to 1 by Gm, right. At low frequencies, of course, the capacitor is an open, so the output impedance is infinite, right, and that is precisely what you see here. At high frequencies where f tends to infinity, this voltage becomes, I mean the impedance becomes simply 1 by Gm, because this second term tends to 0, and the output noise spectral density simply becomes 1 by Gm whole square times 4 kT eta Gm. All right. Now, what we are interested in is the total noise spectral density at the output, and that will be 1 over Gm plus 1 over J 2 pi F R C times Gm the whole square times 4 kT eta Gm. This is the noise contribution due to the OTA, plus we need to add to this the noise contribution due to the plus the integrated transfer function, which is 1 by J 2 pi F R C times GMR by 1 plus GMR the whole square to 4 kT So, this is the contribution due to R, and this is the contribution due to the OT. All right. So, what one would be interested in practice is to compare. Please note that this is the integrator. Okay. And we know what the noise spectral density is here, but what we would like to do is to figure out how this noise spectral density compares in relation to the strength of the input signal itself, right. So, in other words, we would like to refer all these noise sources to the input. In other words, what we are trying to say is that let us find the strength of a single noise source at the input whose effect is to have, or whose effect is the same as that of all these multiple noise sources inside the circuit, right. So, that is what is called the input referred noise source. So, let me call that Vn EQ. The EQ signifies the equivalent single source, right, whose effect is the same as all the other multiple source noise sources in the circuit. All right. So, if one wants to find the strength of the equivalent noise source, all that one needs to do is to observe that the output noise spectrum due to the equivalent noise spectrum, equivalent noise voltage source we have chosen is simply S V equivalent multiplied by mod h of f the whole square, which is 1 by j 2 pi f r c times g m r by 1 plus g m r the whole square times 4 k t r. I am sorry, this must be equal to this, right. So, clearly S V equivalent of f is nothing but you divide throughout by this factor, and when you divide this goes away. So, you get 4 k t r. This makes sense because the noise source corresponding to the resistor is at the same place as the equivalent noise source that you are trying to find. So, it is no surprise at all that 4 k t r appears. All right. The next thing is this factor divided by this, and again let us make a couple of simplifications, assuming that GMR is much larger than 1, I will just simply divide by, I will make this approximately 1, okay, and what happens? For KTR plus 4 KT eta by GM times 1 by GM plus J 2 pi FRC by GM, this the modulus square. All right. Now, our signal exists only at, or rather before I get to that, let me just simplify this by pulling out the 1 by GM common factor, and therefore, this becomes 1 plus J 2 pi FRC the whole square. Our input signal is at low frequencies only, right. So, at low frequencies this is going to be much smaller than unity. So, the input referred noise spectral density at low frequencies is 4 KTR plus 4 KT eta by GM. Understand? And if GMR is much larger than 1, which do you think is the dominant source of noise? The resistor is the, I mean, since GMR is much larger than 1, usually done to make sure that the unity gain frequency of the integrator is 1 by RC. We see that the noise contribution is largely because of the input resistor. Does it make sense? All right. Is this clear? Now, let us see, I mean, we have now understood what thermal noise does to the integrator. The effect of all these thermal noise sources is a single input referred noise source whose spectral density is pretty much that of the input resistor. Okay. But in our sigma delta modulator we have several integrators. Again, let me take the example of CIFF loop. So the loop filter probably looks like this. All right. And please note that we want recall that the first the input stage of the SIF modulator looks like U minus V. So what should we do? How do we sum up U and V? You can add, instead of using a single integrator, I mean you can, instead of using an integrator, you can use a summing integrator by using another resistor like this. For instance, this is U and this is minus V, and you need to have, I am sorry, you need an inversion. So all right, and once you close the loop around the quantizer, the signs must be chosen so that there is overall negative feedback. Okay, you must carefully follow through the inversions and so on. So what do you think the input referred noise of this structure would be? What is the input referred noise of this integrator, or what is the, I mean when referred to its input? Approximately 4 kTR. Now when this noise source is referred to the input of this integrator, what do you think will happen? In other words, what I am saying is that think about it from a block diagram viewpoint like this. You have two integrators, K1 and K2, and you are actually injecting, you can think of this as some noise here, all right. So what is the effect of a noise source here? When referred to this input here, it's S times that noise source. In other words, at low frequencies the effect of this noise here is negligible. And why does that make sense? This block is an integrator which has got infinite gain at DC and a very large gain at low frequencies. So, any inaccuracy here when referred back to the input gets divided down by the high gain of the first integrator. Therefore, the effect of these noise sources, that is those added by the second integrator and subsequently in other integrators or the summer for that instance, when referred back to the input of the loop filter become almost 0, right. So, this means that the only noise source we have to worry about is that of the first integrator. Is this clear? And what do you think is the noise input effort noise of this integrator? Since we said that the noise of the op amp is negligible, let us assume an ideal op amp to begin with. All right. So, what is the input referred noise of this integrator? It is not 4 KTR. I mean, see, you can't say 2 KTR because without knowing anything, right, you have taken in, without this it was 4 KTR, right, you have added one more resistor which produces more noise, correct. So, the input referred noise cannot be smaller than 4 KTR, you understand. If at all, it can only be equal to or larger. Okay. So, let us see what it is. A simple way of doing this, because both the resistors are connected in parallel, is to assume noise current rather than noise voltage. So, the this has got a strength of 4 kT by R noise current. Similarly, this resistor also has got a noise current whose strength is 4 kT by R. So, the total noise current flowing through this capacitor is 8 kT by R. If one had to have a single voltage source whose effect would be the same as the effect of these multiple noise current sources, at the output the single equivalent voltage source here must be able to produce 8 kT by R into the capacitor, correct, and that is only possible when what? Assume these resistors are now noiseless. What is the transfer function from VEQ to this current? the current is VEQ by R is the current through the integrating capacitor. So, spectral density wise I must divide by 1 by R the whole square. So, SVEQ of F is nothing but 8 kT into R. You understand? Is clear? So, to summarize the discussion on noise, what dominates the input referred thermal noise of the modulator? The first integrator input referred noise is approximately equal to the input referred noise of the modulator. Okay. Now, this can be used to advantage in the sense that the noise of this integrator and this summer does not matter. So, one can deliberately make them more noisy. And what is the advantage of making them more noisy? Pardon? You can't make, I mean, how can you make something more noisy and expect better performance? What are you gaining?
You can have a lower
Design.
Design is not any easier than.
Low gain can you can use.
If you have a circuit which is noisy and if you want to get half the noise, what will you do? I will take two identical circuits and connect them node to node in parallel. That will reduce the noise by a factor of noise spectral density by a factor of 2 while doubling the power dissipation. This you are aware of, right? So, designing something which is noisy is as difficult or easy as designing something which is less noisy, because it is just a matter of copy, paste and connect multiple copies in parallel, alright. So, turning this discussion upside down, if you want to, if you double the noise power, and that is done by taking the circuit, chopping it up into two identical halves and getting rid of one of the halves. So, the noise is now 3 dB worse, right, whereas power dissipation is 1/2 of what it would be before. So, since we know that the noise of subsequent integrators do not really matter, because when referred to the input of the modulator they get divided down by the high gain of the first integrator in the signal band, it is acceptable to make them deliberately noisy, right, and gain in the form of power dissipation, right. So, in other words, if I took this integrator, chopped it up into n parts and threw away n minus 1 of those parts, what will happen to this resistor here? It will become n times R. What will happen to this capacitance C? C by n. Now, and what will happen to this current? This current has reduced by a factor of n. Since this current has reduced by a factor of n, the current that the op amp needs to drive has also reduced by a factor of n, and therefore it makes sense that you can make the op amp n times smaller by reducing all bias currents in the op amp by a factor of n. So, the op amp power dissipation was also reduced by a factor of n, right. So, it is therefore commonplace to choose the impedance levels of subsequent integrators and whatever else comes after the first integrator to be much higher than what you would choose for the first integrator, because A, you save power, you will get more noise. However, when you refer that back to the input, it does not matter. You understand? So, the noise of the first integrator is a crucial factor that affects the input referred noise of the modulator. Does it make sense? Now, we have several noises to deal with, right. The total input referred or the total noise at the output of the modulator consists of two components. What are the two components? Okay, I mean, and what else? I mean, you are taking this and embedding it inside a sigma delta loop, correct? So, the total in band noise consists of thermal noise from the loop filter, which, as you all say, largely comes from the first integrator, plus in band shaped quantization noise. And since thermal noise and quantization noise are independent of each other, you can simply add their noise powers. You understand? All right. So, the peak SNR of the modulator is therefore the maximum stable amplitude MSA whole square by 2, and why is this whole square by 2? It is a sinusoid, and then the mean square value of the sinusoid is amplitude square by 2, and this divided by the noise power, which is thermal noise, which is largely, in the example we have taken, is 8 kT times R times, that is the spectral density. To get the power, you have to multiply it by the bandwidth plus in band quantization noise. All right. Please note that this everything is under our control, right. This can be reduced one can keep this the same and reduce the thermal noise by impedance scaling the first integrator. One must bear in mind that reduction of the impedance level means increase in the power dissipation by the same factor, all right. Specifically, doubling power in the first integrator will cause the thermal noise to noise power to go down by a factor of 2, all right. One can also keep the thermal noise fixed and reduce the in band quantization noise, all right. And how will one do this? There are many ways of doing this. You either increase the order or increase the out of band gain or a combination of the above, and therefore the in band quantization also can be, noise can also be varied. Now one obvious question is, if I want to shoot for a certain signal to noise ratio, is there, I mean, should I make my modulator be limited by thermal noise or be limited by quantization noise? You understand, to achieve a certain signal to noise ratio, it means that I must achieve a certain in band noise. The in band noise consists of two components, one is thermal noise, the other is the shaped quantization noise. Thankfully both of them are independent and are can be controlled independently. The thermal noise can be controlled by simply impedance scaling the first integrator. The shaped quantization noise can be controlled by changing parameters of the noise transfer function in ways which you are all aware of by now. Now can we comment on what strategy one would use in practice? Do you think I should choose the in band quantization noise to be much larger than thermal noise, or should I choose, you understand, I want this level of thermal noise of total noise, right. This can be, I can think of at least 3 scenarios how you can realize this. This much can be thermal noise and this much can be quantization noise, all right, or this much can be quantization noise and this much can be thermal noise, or both of them can be the same. Q T, let me exaggerate this a little more. So which do you think makes most sense to do? You want more quantization noise and less thermal noise. Why does this make sense?
If we have less quantization noise means the design of the quantizer is more difficult.
Quantization noise depends on overall modulator design.
Yes,
So
sure.
it is difficult.
Well, okay, so this is the desired total noise. Okay, I mean, you all understand the question, right? The total noise is so much and that is derived from the spec of the SNR. You want that to be some level. The question now is, does it make sense to make it all thermal noise or all quantization noise or both of them equal?
relatively how much power you have to spend to reduce quantization noise, or how much power you need to spend to reduce thermal noise.
Okay.
Only
So
when that ratio is known, you can decide on it.
okay. So great. So the what he is saying is the following. When you say what is the best thing to do, it obviously this has to do with power efficiency, correct? Because to reduce thermal noise, there is an implication. If you want to reduce thermal noise, you must increase power in the first integrator. I mean the other integrators are are total non-entities as far as input effort noise of the whole modulator is concerned. Okay. To reduce quantization noise, what should one do? I mean, do you think there is a power penalty associated with increasing quantization noise? No, one can easily increase the reduce the quantization noise by, for instance, mildly changing the out of band gain of the noise transfer function. You understand? Of course, one could go and design a more complicated quantizer, but that is not necessary. So, in other words, to reduce quantization noise, it is very easy from a power point of view. Of course, one requires to design a more aggressive or slightly more aggressive noise transfer function, but there is in principle no power penalty associated with reducing the quantization noise. However, there is a big power penalty associated with reducing the thermal noise. To reduce thermal noise by a factor of 2, you need to double the power dissipation of the first integrator, right, whereas to reduce quantization noise by a factor of 2, you do not have to do anything as far as power dissipation is concerned. So, what does this mean? Now that you know this, does this make sense to make the input noise largely thermal noise or largely quantization noise? Largely thermal noise, right, because if you choose the opposite, then the power dissipation is unnecessarily large, right, whereas it is very easy to get rid of quantization noise by simply changing parameters of the noise transfer function. So, you always want to make sure that the thermal noise dominates the input effort noise of the quantizer of the modulator. So, okay. So, it is common practice to choose thermal noise to be about 15 to 20 dB greater than the shaped quantization noise. So, the noise power of the thermal noise is 10 times larger, I mean at least here it must be about, this means about 30 to 100 times larger in power terms when compared to the quantization noise. Okay. This has got other benefits in the sense that the input to the quantizer is now also got a random component due to thermal noise. Okay. So, the quantization error is also becomes less periodic because of this random thermal noise that the device noise adds. Understand? And of course, from a power point of view, this makes a lot of sense because you do not, you know that it is very easy to reduce quantization noise power by simply making the noise transfer function more aggressive. So, this concludes all that I had to say about noise in the integrator, noise in the modulator, and how one would choose the levels of thermal and quantization noise. Thank you.